Welcome back. Now we can look at how you can actually use a rice table to solve for some numeric data, for some quantitative data. So this question says calculate the H+ concentration of a 0.37 molar solution of acetic acid. And I've already provided you with the formula for that. And then I'm also giving you the Ka. And remember, the K is a number that can be looked up in a chart. So if you can look it up in a chart, then you don't have to memorize it. And this number is different for all different kinds of acids. So Ka for acetic acid is 1.8 times 10 to the negative 5. Okay, so to do this, anytime I'm looking for the H+ concentration of a weak acid, I gotta do several steps, but we've kind of been working our way up to this. First thing you gotta do, write the dissociation equation. And then the next thing that always kind of goes along with that is write a K expression. So let's do those first two things. So the dissociation equation for acetic acid. HC2H3O2 is a weak acid, and I know it's weak because it's not strong. And so I use double-headed arrow, and that dissociates into, I know it's an acid, so it's going to give me an H+, and it's this H at the beginning is the one that's going to come off. It's what we call the acidic hydrogen, leaving us with the acetate ion, H3O2 minus 1. And this is all 1-to-1. So there is my acetic acid dissociating to H+ and acetate ion. And then my K expression for that, K, and this is a Ka because it's an acid, equals H+ C2H3O2 minus all over HC2H3O2 no minus, just bracket. And remember, this is products over reactants and raised to their respective powers, which when this is balanced is just 1-to-1-to-1. So there's the first two things you got to do. Write the dissociation equation, write the K expression, and then what follows from that, what we did in kind of the beginning of this lesson, fill out a rice table. So let's do a rice table for all of this stuff. So let me get my space going here. So remember, R is the reaction. So here's my dissociation equation. And I didn't write this in a way where I could have kind of used it over here and not had to rewrite this. That would have been nice. And then I is initial concentration. So before this thing dissociates, how much or what is the concentration of it? And that is given to us in this question, 0.37 molar. And before this breaks apart, since it's still together, that means we have 0 concentration of these. The change that occurs when this breaks apart, it is going to decrease in concentration. I'm not going to have as much of it, so we put negative, but we don't know by how much yet. That's actually what we're going to solve for. So we decrease it by X, and when this breaks apart, these two things are going to increase because this is forming those. So they increase, and everything's in a 1-to-1 ratio, so they increase by X amount. And then my equilibrium line is just adding I and C together. So 0.37 minus X, 0 plus X is just positive X, and again here. So there's my rice table. The fourth step, and this is what's new in this video. So the fourth step is we're going to make some substitutions. So we're going to substitute the stuff from the E line into the K expression. So what I mean by that is I'm going to take everything right here and I'm going to substitute it in to that K expression respectively. So for the HC2H3O2 part, which is down here on the bottom, I'm going to write 0.37 minus X. For the H plus part, Up here on the top, I'm going to write x. And then for the acetate part, also up on the top, I'm going to write x. So my new K expression looks like this. Ka equals x times x over 0.37 minus x. So there's my new Ka expression. And then two things here. We are gonna use a little bit of algebra. So that's kind of our last step, algebra. Meaning we're gonna solve for x. And so in order to solve for x, that means I gotta know what K is. Well, I already told you what K was. So I can take all of this jazz and set that equal to what that K value was, because I know what that number is. So now I have x times x over 0.37 minus x equals 1.8 times 10 to the negative 5. So now I can algebra this, but the thing about algebraing this, when you start to gather like terms together and try to get x by itself, you're going to find that to solve this, you end up with a quadratic problem, and you would have to use the quadratic equation, because you're going to have an x squared term and then an x to the first power term. And so there's something that we can do here with regards to this x. What we're going to say is that this x term is super small. And it is. It is very, very small. It's a very small number. It's so small, in fact, that it doesn't really impact how things change here. So on this bottom, this number is going to be super duper small compared to the 0.37 that we call it negligible. And if you're not familiar with that word, negligible, that just means that it's so tiny that it doesn't really matter. It's like saying, what is the volume of one drop of water in comparison to the size of the ocean? Well, that one drop of water does change the volume of the ocean, but not so much that we can even notice that it changes it. It's super duper small amount. So when I do that, when I call this x negligible, I'm going to rewrite this and kind of simplify some terms. So x times x is x squared. That is over top of 0.37, and I'm going to get rid of that minus x because we called it negligible. It's so tiny. And then all of that is equal to 1.8 times 10 to the negative 5. Now from here, this algebra should be pretty simple for you. I'm going to move my 0.37 over to this side. So I'm going to multiply this side by 0.37, and I'll multiply this side by 0.37, effectively canceling that. So handy dandy little calculator, 1.8 times 10 to the negative 5 multiplied by 0.37. That is a horrible, horrible example that I chose there. So we're going to say this is 6.7 times 10 to the negative 6, and that's all equal to x squared. Well, now to get rid of the square, we just square root both sides, and I get x equals 2.6 times 10 to the negative 3rd. Okay, so at this point, you've solved for x, which is awesome. You did good. You did great. That's what x is. But this question says calculate the H plus concentration. Well, here's the thing. H plus, we assigned to be represented by x. So when you find x, that is the same thing as solving for H plus. That is what x represents. So the H plus concentration is in fact 2.6 times 10 to the negative 3rd. And since this is concentration, this is molarity, big M. Very good. So there's the steps, and those are in writing on the your steps slide. Always write the dissociation equation, the K expression, and a Rice table, and we've gone through that. But then the new stuff is then you take the E line and substitute it into the K expression. So take everything from your E line, plop it into that K expression, call the X on the bottom that X on the bottom, only that one. You don't want to call these guys negligible. Only this one that's being subtracted here. We call it negligible because it's ridiculously small. And then we do a little bit of algebra to solve for X, which in this case was the variable we used to represent H plus. This question could go on, and I did put one in the your turn, to say further. It could go on to say, I want you to tell me what is the pH. So what is the pH of this acid, 0.37 molar acetic acid? To find the pH. Well, to find the pH, all you really have to know is the H plus. And we just went through a bunch of steps to calculate the H plus. Once you know H plus, think back a few weeks, reference your pH diamond. So if you know H plus, to solve for the pH of that, pH equals negative log of the H plus concentration. So if I take the negative log of the H plus concentration, which is negative log of 2.6 times 10 to the negative 3, that will tell me my pH. That's somewhere around 2 point something. Negative log 2.6 E negative 3 equals 2.59. I'm going to go out 2 decimal places here. There's a special sig fig rule about pH that you'll learn when you take AP if you choose to do that. So 2.59. So if this question went on to say, what is the pH of this guy? Then you just take the negative log of the H plus. What if it's asked you, like maybe you solved for, this was a base and we solved for X, but this was OH minus. You can still use your diamond. If you have the OH minus and you want to find the pH, that's just a 2-step process to get there. And it doesn't matter which direction you go. So there is one on the your turn that just asked you to find H plus. So just solve for X, work through these steps. And then there's another one that asks you to do the second step, where once you find the H plus, determine what is the pH of that. So good luck, and be sure to check in with your teachers on Zoom if you get stuck or have any questions, and have a great day.